Hi, my name is Muchin, and here I'm presenting my project for EECE 570. My project is Sketch2Slide, and as you can see from the aesthetics, it turns Sketch into slideshows. The motivation is that, usually we're visual learners, but PowerPoint encourages passive learning as most of them are boring. They're also time-consuming to make if we want to convey an idea. In person, in classrooms, for example, we resort to sketching on paper or whiteboards. In the age of learning or working from home, we want an ease of use of paper and pen. And Zoom doesn't count because the Zoom annotation really just sucks. So, how does this work? Well, one, you sketch out the slides on a piece of paper and then take pictures of them. Two, run this program. Three, export to file and refine and customize the slides. So the problem is broken down into three layers. One is that on the very outside we have this app wrapper, which must be easy to use. It's basically just images in, PowerPoint out. In the middle we have some color correction and presentation refinements, such as we must ensure that it has a high contrast and the colors are accurate. And lastly, at the core of the problem is robust and accurate document detection. This has to be robust against different background lighting and different mediums such as paper, whiteboard, or tablet. So this is the high-level overview of this project and kind of defines the overview of this presentation. So first we have some images in, and it goes through 4 phases. First phase is document detection and quadrilateral rectification to straighten out the image, and then we do some post-processing to make sure the colors are accurate, and also we can, and next we extract regions and do some layout, and lastly we export to file. So in terms of document detection, the goal is to obtain the geometry boundaries of this piece of paper or a whiteboard, etc. The core steps is 1, we want to segment the document from the background, and 2, find the edges that define the boundary. Now this is kind of challenging because in a lot of cases we have either poor lighting, occlusion to the hands or people, similar luminosity, for example in this case, between the paper and my shirt. There are also misleading lines in the other parts of the image that might mislead the line detector. So that's enough highlighting. Let's dive into the details. So the first thing we consider is the HOUGH transform. As we learned, HOUGH transform takes pixels in spatial space and transforms them into row and in terms of row and theta. For RGB and binary image, this does not reveal a lot of usable information, and it's a lot better if we use a gradient or an edge filter. But as we can see here, near areas with similar luminosity, the gradient don't do so well. So in the end, I ended up using an Sobel edge filter. Through experimentation, I also learned that because the document takes up most of the screen space, downsampling the image to a much smaller size actually makes this detection much more robust and less sensitive to a lot of distracting backgrounds. I also resize it into square images if it's not in square. Then, to find the peaks in the HOUGH space, traditionally, for points, they on the accumulator, they use the constant ratio R. But, if you use a constant ratio, then the number of peaks that come out can vary, and it's not very robust. So I devised a binary search algorithm to find an optimal ratio R, such that 4 confident peaks can be picked. And if this fails, then we fall back to previous method. In peak search, one problem is that certain clusters of values, for example, these wavy lines here, are very close in value, so it can actually throw off the peak picking. The workaround to that is using an absolute gradient of the accumulator, as you can see on the right, which makes finding peaks a lot easier. As you can see, these points are very highlighted. The downside is slightly more expensive, but it works. Another problem is that there are too many points here, but lower resolution of the HOUGH space doesn't really work because it also means we lose accuracy in line detection. So we use morphological dilating on these bright spots so that we get exactly 4 regions, and then we erode them to a single pixel for each region, yielding us exactly 4 pixels. These 4 pixels, or peaks, corresponds to 4 unordered lines in spatial domain. So we choose two of the lines we choose a combination of the lines and find the intersection. Then for each of these intersection points, we will reorder the points into control points using in this order, 1, 2, 3, 4. These control points can then be used as reference to do image rectification. And the goal is that knowing these control points, M's, then we can find the inverse projection to find these big M's. And the projection matrix looks like this, where E and F influences the vanishing point, or basically how skewed one side is. Then we rescale the image with 16:9 or 4:3 aspect ratio. That is user configuration. So here's an example. This is the original image. We find the intersection points, and this is the rectified image. And lastly, we use the control points. We use transform control points to crop the image to just the document. Here's color correction. So now let's talk about color correction. This is the next phase.
Oh, this one's
From the cropped image, we use adaptive thresholding to segment document content from document background. Now, if the background is mostly neutral, as we see here, then we can find a transform T that equalizes the highlights in each color channel. In this case, look at this color in the background. It's not the RGBs; they're pretty separated and not very good. So then we apply this transform to the entire image, and we basically corrected the here. And as you can see that in histogram, we also have it lined up. In terms of tone curve, I experimented 4 different curves to enhance the image a little bit further. One is identity or no change. Sinusoidal S-curve as indicated by green. Parabolic as indicated by purple. And piecewise steep sinusoidal S-curve, which is same as sinusoidal except steeper. Here are the results. Turns out S-curve is pretty good. Parabolic is pretty good also, but it kind of kills a lot of detail, especially if they're drawn or written in lighter colors. Steep S unfortunately has this discoloration in document content, but the background looks better. In the end, I decided to go with none of these, except for the identity, because these actually is quite expensive calculating the tone curves, and sometimes simplicity is key. So lastly, we do this foreground boost. Knowing the background foreground segmentation from earlier, we can use it to brighten the background and boost the contrast of the foreground separately. And this is the final result for that particular image. Lastly, the next step is to region extraction. So we inverse the background segmentation and use rectangular morphological dilation to bridge between the letters so that it all appears as the same region. Then we remove the regions touching the edges, and then we can obtain bounding boxes for each of the regions and then write them as a metadata file. And for each regions, we can also write each image as a sub-image to file. And this can feature the alpha channel or transparency, which is useful. Now note that because we know that these individual sub-images, since they're nicely separated and saved, not implemented here, but potential extensions could be image or text classifiers or text recognition, semantic analysis. It's your imagination. Lastly, the file is exported using python-pptx. I wrote a Python code that takes the metadata exported from region analysis and assemble the PowerPoint file using the location and size informations. It's organized based on the order of image capture and exported using 16:9 or 4:3. So you can see here writing the code. It's very simple and very fast. And here's a demonstration of the exported slide. You can see here each of the regions has its transparency, and you can move them around. And because it works so well, the first 7 slides of this presentation actually comes from these images, and are entirely unedited. And thank you.